Trigonometry, Chapter 8, Section 8, Harmonic Motion. Okay, we're going to talk about simple harmonic motion in this section. First of all, we have an illustration of a spring that is bobbing up and down, and you may have actually encountered this in physics already, or you may study it in physics this year. But illustration part A there, capital A, shows a weight. It's attached to a spring in its rest or equilibrium position. In other words, it's just sitting there. It's not been stretched. It's not been compressed. It's just resting. If the weight is pulled down and let go, its oscillatory motion, neglecting friction, is described by a sinusoid. In other words, the up and down motion of it can be described by a sinusoid or a wave that is shaped like a sine curve. Now notice we are neglecting friction, and we're going to talk about what friction does to it in a little bit. But the up and down bobbing motion can be described by a sinusoid, which means we can describe it with a sine equation. Other applications of this type of motion include sound, electric current, electromagnetic waves. Okay, let's look at it on a circle. Suppose the point P, which has the coordinates x, y, moves around the circle counterclockwise, so in a positive direction, at a uniform angular speed omega. So kind of imagine that the circle is like a wire and P is a bead, and you are sliding P, the bead, around on this wire, and you are going in a steady, consistent angular speed. The coordinates of the point at any given time as you go through this motion are going to be a cosine theta, which would be a times omega theta, and y will be a sine theta, which would be a sine omega theta. Okay, and a is the radius of that circle. So it doesn't have to be a unit circle, it can be a circle of any radius a. Now, as P moves around the circle from starting position at A0, the point 0y, so look at the corresponding y values, really what we're looking at. Look at the point Q on the y-axis, okay, which is representing the y value of the bead, of the point that's moving. That is going to go up and down as the point goes around that circle. It's going to oscillate from 0A, that's going to be at the high point, and then when the bead gets all the way down to the bottom of the circle, then it's going to be 0, negative A. So in other words, the y value is going to go up and down between negative A and A. Similarly, the point R x0 is going to oscillate between A0 and negative A0, so the x value is going to go back and forth between negative A and A also. And this is called simple harmonic motion. Now, a few things about simple harmonic motion. The amplitude of the motion is A. We've talked about amplitude before. In a sine curve, it represents half the distance from the lowest to the highest point, or the distance from the middle to the highest point. The period of the motion is 2 pi over omega. One complete oscillation is a cycle per period. The number of cycles per unit time is called the frequency. So how many cycles go by in whatever unit time is, a second, a minute, an hour, is the frequency. And you find that by doing omega over 2 pi, which is the reciprocal of the period. The position of a point oscillating about an equilibrium point at time t can be modeled by S of t equals a cosine omega t or a sine omega t. A and omega are going to be constants. Again, a is your amplitude. Omega is the angular speed, how fast is it moving. The period is 2 pi over omega, which shouldn't surprise us because remember when as we've studied these equations, the period is always going to be 2 pi for sine and cosine, 2 pi over whatever that number is in front of the x, or in this case the t, and then the frequency, you just flip that upside down. Now, if you're wondering, well, which do you know, how do you know what to use? Are you going to use the cosine or the sine? The answer to that is it depends on where the motion starts. If the motion starts at rest or at 0, then you're going to use sine because the sine curve starts at 0, 0. If you're going to start the motion at either the highest or lowest point of the motion, then you're going to use cosine because a cosine curve doesn't start at 0, it starts at 1. So let's do an example. Suppose you have an object that's attached to a coiled spring. It's pulled down a distance of 5 units from equilibrium and then released. The time for one complete oscillation is 4 seconds. You're going to give an equation that models the position of the object at time t, determine the position at 1.5 seconds, and find the frequency. So really the big thing here is A. If you've got A, B and C are going to follow. Now notice that we are starting this motion not at rest, but pulling it down 5 units. Pause the recording, give this a try, and resume to check your answer. So when we start, the displacement is 5 inches below the equilibrium. In other words, we have pulled it down by 5. So S of 0 is -5. So our A is going to be -5. We're going to use cosine because we are not starting at 0. We're not starting at rest. We're starting below it. So we're going to use cosine. The period is 4. It told us that. So that means 2 pi over omega equals 4. We solve for omega. Omega is pi over 2. So the motion is -5 cosine pi over 2 t. After 1.5 seconds, well, this is easy. If we got A, this is easy because you're just going to put 1.5 in and put it in your calculator. And so we have 3.54 inches, which means this is above the rest point. It has moved up above 0. The frequency is the reciprocal of the period. So the period was 4, so it's going to be 1/4 cycles per second. Okay, let's suppose that an object oscillates according to this model. So this time we have the equation, but we're going to pull it apart and analyze what the equation means. So you're going to tell me about the amplitude, you're going to tell me about the period, the frequency, all that good stuff. Just pause the recording, give it a try, and resume to check your answer. All right, so it's modeled in the form sine of t equals a sine omega t. So A is 8, which means it's oscillating 8 feet in either direction from the starting point. So at rest is 0. It's going 8 up and 8 down, or 8 left, 8 right, whatever direction the motion is going. It's going 8 away from rest in both directions. The period is 2 pi over 3 over omega, which is 2.1, and that's how many seconds it takes to complete one complete cycle. And then we flip that upside down and we do 3 over 2 pi, or you could do 1 over 2.1, and that gives us 0.48 oscillations per second. So every second it's going through 0.48, almost half of one of these oscillations. I'm going to talk about damped motion. So far we've neglected friction in these examples. What friction does is it slows down the oscillations. If you think about it, when you pull a spring and let it go, it's going to bob up and down for a while, but eventually it's going to slow. The height is going to decrease, the amplitude is going to decrease, and it's going to eventually stop. And that's because of friction, whether due to the air resistance or whatever. Friction is going to slow things down and decrease the amplitude. And we've been neglecting that so far. So we say that when something outside interferes, like friction, that the motion has been damped. And the figure shows how e to the negative x sine of x is bounded above by e to the negative x and below by negative e to the negative x. So when you have a function multiplied in front of the trig function, you have something with an x, like e to the negative x, multiplied by the sine of x or the cosine of x, what happens is the sine or cosine curve gets trapped in between that function that's being multiplied by it and the negative of that function. And if you were to graph this on your calculator and kind of enlarge it, you would see the sine curve kind of still winding in there between those two other curves. It's still going, but it's eventually going to flatten out. It's eventually going to get crushed in between those two curves. And that's what friction does, and that's what the damping factor will do to a typical example is the one we just saw, e to the negative t sine t. And here's a little bit bigger picture of it. You can see the normal sine curve in blue, and then you have the e to the negative t above and below it, the positive and the negative, and you see the effect that it has on the sine curve. The curve can only go up and down so long, and then it gets kind of sandwiched in between. An example of damped oscillation would be shock absorbers that are put on automobiles to dampen the oscillatory motion and give you a smoother ride. Additional practice, believe it or not, we are done with this section. Not only done with this section, but done with this chapter. So for the rest of this, actually I think there's only a couple of problems here. Pause the recording, give the problem a try, resume to check your answer, and continue until you're finished.